Hey everybody, thanks for joining us in this video about Newton's third law. Now I've already made two videos talking about Newton's first law and second law, and I've also made a bunch of other videos about forces, so if you want to go check those out on my channel, go ahead and do so. And if at any point I say something that you like in this video, go ahead and hit the like button down below. And if you want to see more content from me, go ahead and hit that subscribe button. I'd really appreciate it. But anyway, today we're going to be talking about Newton's third law. And everyone always simplifies Newton's third law down to, for every action, there is an equal and opposite reaction. I'm sure you've probably heard that at some point in your life. And this makes sense, and this is true for Newton's third law. It just sometimes makes a little bit more sense if I can go in depth on Newton's third law and explain it a little bit more technically than just this statement. So a little bit more technical rendition of Newton's third law. And it says, if object 1 applies a force on object 2 applies an equal force on object 1 in the opposite direction. So that means if you're applying a force to anything, that object is applying the same amount of force back on you. So this particular statement can imply two different things. One of the things that it can imply is that no force acts alone, which means all forces come in pairs. And I kind of feel like Newton's third law is best explained with a lot of examples, and maybe these examples will help make sense and solidify Newton's third law and the fact that no force acts alone, and every time you apply a force to something, the same amount of force is applied back on you. So let's look down here, and I have the example of a hammer and a nail. Now a hammer and a nail is a pretty good example of Newton's third law. So a hammer will apply a force downwards on a nail. So we could call this force right here, force of the hammer on the nail. Now with that said, there's an equal and opposite force going back upwards, and this would be the force of the nail on the hammer. Now some people are still skeptical at this point, but they look at this and they say, but the hammer is applying a force to the nail. How is the nail applying a force back on the hammer? Well, according to Newton's third law, the force of the hammer on the nail is equal to the force of the nail on the hammer. Now, it's easy to prove that the nail is applying a force back on the hammer. And the way I can prove that to you is the fact that the hammer's motion changes whenever it strikes the nail. When it comes into contact with the nail, the motion of the hammer changes. And that's a connection back to Newton's first law, where an object in motion wants to stay in motion unless acted on by an outside force. So in this case, when the hammer hits the nail is now an outside force on the hammer, and the hammer was in motion, and when it came in contact with the nail, it would come to a stop. Now, another interesting connection with this and another one of Newton's laws is a connection with Newton's second law. And Newton's second law says force is equal to mass times acceleration. So in this case, we can say the force of the hammer on the nail incorporates the mass of the hammer, and the acceleration the hammer experiences is going to be equal to the mass of the nail and the acceleration that the nail experiences. Now, a really important key fact in this is the fact that the hammer has a lot larger mass than the nail. So the hammer has a very large mass, and because of that, it's going to experience a small acceleration. So a very, very small acceleration for the hammer. But the mass of the nail is very, very small, and therefore it's going to experience a very large acceleration. So when a hammer collides with a nail, the forces between the hammer and nail and hammer, whichever way you want to go about it, are the same. It's just that the nail is going to experience a lot larger acceleration than the hammer does. And with that concept in mind, I want to bring up another interesting situation where this would happen. Now in football, Newton's third law is extremely important. And we have two players here. We have James Harrison and we have Colt McCoy. And these two guys collided into each other. We might say that there was a force between these two guys. And clearly, one person is winning in this force collision that's happening. So James Harrison over here, he weighs about 245 pounds, somewhere around that. And Colt McCoy here, he weighs somewhere around 220 pounds. So neither one of these guys are really small guys. They're actually both pretty large. But you can see the importance of being a big guy in football, because whenever you come into a collision with someone, you can change their motion a lot easier than a smaller person can. Now, that's not to say small people can't win a collision battle, but in this particular situation, that did not happen. In fact, more times than not, the bigger person wins in a collision than a small person. And by winning, I mean changing the motion of the other player. So anyway, these two guys collided and there was a force between them. And the force that James Harrison applied is equal to the force that Colt McCoy applied back. However, James Harrison is still connected to the ground and Colt McCoy's feet are flying through the air. Anyway, the force of James Harrison on Colt McCoy is equal to the force that Colt McCoy applied to James Harrison. However, the mass of James Harrison was larger, therefore he experienced a smaller acceleration. And the mass of Colt McCoy was smaller than James Harrison, so he experienced a larger acceleration. And remember, acceleration can be speeding up, slowing down, or changing direction. And the larger mass something has, the more inertia it has, which means the harder it is to change its motion. So it's harder to change James Harrison's motion in this situation than it is Colt McCoy's. However, being big in football is not always the most important thing. There's actually a guy who played football who was small, and he used it to his advantage, and his name was Barry Sanders. Now, I have another video over here talking about Barry Sanders and the physics behind him, but simply, Barry Sanders was a small guy, and he would use that to his advantage so that he could change his direction faster than anybody else on the field. And whenever he's changing his direction faster than anyone else, no one can get a good hit on him, no one can really grab him. Now, if you ever watch Barry Sanders play, he very rarely tried to run into someone head on, because Barry Sanders probably knew something along the way of Newton's third law, because he knew that whatever force he applied, the other person was going to apply the same amount of force back. And chances are the fact that he's very small, he's going to experience a large acceleration, and these other guys on the field are much larger than him, so they're going to experience a smaller acceleration. And therefore, he would lose those battles if he was in collisions with guys. However, Barry Sanders used his small mass in order to change his direction a lot faster than the other players could, and so he was able to avoid a lot of tackles that way. Anyway, let's talk about another example. Let's talk about a guy who's riding a bike down the road, or in the grassy field, or whatever. Now, the biker has a velocity that is going forwards. And what is creating this motion that makes him go forwards? Well, to understand where that motion is coming from, you got to focus on this back tire back here. And this back tire is where all the magic happens of his motion. You see, the tire is rotating in a clockwise direction, which means this connection point right here between the ground and the tire is very important. That's where all the force is being applied. Now, the back tire is applying a force backwards on the ground. So we can call this the force of the bike on the ground. However, we know all forces come in pairs, and there's always an equal and opposite force being applied. So that means the ground is applying the same force back on the bike. So we have a force of ground on the bike. And that force from the ground on the bike is what creates that forward motion. You see, the tire is pushing backwards on the ground, but the ground is pushing forwards on the bike. And here's the thing, the ground is connected to the earth, which is a very, very large mass, so it's going to accelerate very, very little. So let's write that down. The force of the ground on the bike is equal to the force of the bike on the ground, but the ground, which is, well, the earth, has a large mass, and it's going to experience a very small acceleration, and the mass of the bike is much smaller, therefore it's going to experience a much larger acceleration. So Newton's third law is saying that all forces come in pairs, and every force is equal and opposite to each other. But you can't forget Newton's second law and the fact that force is equal to mass times acceleration. Let's go down and talk about one more example, and this one is one that really confuses people. And I've had a lot of conversations with my friends about this exact scenario. And it actually has taken me a long time to really get a good grasp on it and understand why this scenario works. And when you're pushing against a wall. So if I am pushing against a wall, I am applying a force to the wall. So this would be the force of the person on the wall. But that wall is going to be applying a same force back on me. So this would be the force of the wall on the person. And we know that these two forces are going to be equal and opposite to each other. However, typically when you push on a wall, there's no motion. Now, why is there no motion? And the key part in that is the fact that you are both touching the same surface. When the person is getting a force applied backwards on them, well, there's some friction on the ground that is applying a force forward again. And the same thing is true for the wall. The wall is connected to the ground, and that's applying a force of friction in the opposite way as well. So if we were to focus just on the wall, we see that the force that the person is applying to the wall is going to actually be equal to this friction force down here as well. So there's no change in motion there. There's an equal balanced force there. And the same is true with the person over here. However much force the wall is applying backwards on the person, friction is applying that same amount of force forwards on the person. Anyway, guys, hope that video is helpful in helping you understand Newton's third law. If this helped you at all, just go ahead and hit that like button. If you want to see more content, hit subscribe. Thanks for watching. I'll see you in the next video.